Hey there, this is Chipmunk Math, I'm Vince, and in this video we're going to learn about the Pythagorean Theorem. So let's start off by looking at how a right triangle works. And remember, a right triangle is just any triangle where one of the angles is at 90 degrees. So say that we have this right triangle and we wanted to stretch out that right side, that vertical side. So if we kept the base from moving, what would happen if we were to stretch out that right side? Well, it's got to be the case that the diagonal winds up getting longer to compensate, right? If that diagonal weren't to change its size, then what we'd wind up having wouldn't be a right triangle anymore. Heck, it wouldn't even be a triangle. We just have this thing sticking out up there. So we've got to have the case that one of the other sides changes if one side changes. Similarly, if we went back to where we started and we had that vertical get longer again, but we kept the length of the diagonal the same, we didn't allow it to change, then it's got to be the case that the base shrinks to compensate, right? If one side of the right triangle changes, we've got to have change occur somewhere else. There's a relationship between those three sides. That's the important thing to take away here, is that when you're looking at a right triangle, there's a relationship between the three sides of the right triangle. One of them can't change without affecting the others. So before we go on, let's get some names for these sides so we can talk about them a little more precisely. First, what's that diagonal called? We call that the hypotenuse. So the hypotenuse is the side that's opposite the right angle, and that's always the longest side for a right triangle because it's opposite the biggest angle in a right triangle because that's the 90-degree angle. Now, the other two sides, we just call them legs. So if we're talking about just one of them, we call them a leg. Both of the legs are always shorter than the hypotenuse, and they're just opposite the angles that aren't the right angle. So we've got the hypotenuse for that long side, the side that's opposite the 90-degree angle, and then the legs are the other two, the ones that are shorter than the hypotenuse and opposite the non-90-degree angle. So what is this relationship between the sides? What is that precisely? So for this, we're going to call out some names for them. Let's call out the legs A and B, so that the length of one of the legs is A, the length of the other leg is B, and then the length of the hypotenuse, continuing on with the alphabet, is just going to be C. In that case, it's simply this equation, a squared plus b squared equals c squared. So notice how the legs on the short sides are together on one side, right? We've got a and b are on one side of the equation, but then the hypotenuse, the long side, is alone on the other side. They've all got squares on them, but I want you to notice how the legs always stick together on one side when we're working with this relationship, and the hypotenuse is alone on the other side. We call this relationship, we call this equation the Pythagorean Theorem. Now, you might not have ever heard of this dude before, but Pythagoras is where this is named from. Pythagoras was an ancient Greek mathematician. Now, you'll often hear that the Pythagorean theorem was first invented or come up with by Pythagoras, but that's actually not the case. Pythagoras wasn't the first person to notice this special relationship, this a squared plus b squared equals c squared, the fact that the legs connect to the hypotenuse in this special way. He wasn't actually the first person to notice it. But what he might have been is the first person to prove that it was always true, that you can't get around it, that it always is the case that a squared plus b squared equals c squared, and there's no exceptions to this rule. Regardless of whether or not he actually did it or somebody else did it first, by tradition, just historically, we name it after him. So Pythagoras, we've got the Pythagorean theorem named in a traditional honor of him. All right, so what is the Pythagorean theorem? It's that for a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares, the lengths of the other two legs. Now, that's obviously a bit of a mouthful, but that's kind of how you'll see it written out in a textbook. So let's go through and decode that a little bit. So if we put out side lengths on those, right, we put A and B and C to talk about the three side lengths that we've got there, then the right triangle, the square of the length of the hypotenuse, well, that would be C here. So C squared, the square of the length of the hypotenuse, equals the sum of the squares of the lengths of the other two legs. So the other two legs are A and B, so the squares, a squared and b squared, the sum of the squares, a squared plus b squared. So what we've got is c squared equals a squared plus b squared. Now notice, when I gave you that equation at first, I said a squared plus b squared equals c squared, and that's how we're going to usually talk about this. That's almost always how you'll see it written out, but for some reason in a lot of math textbooks, you'll wind up seeing the sort of written out version of it with words, having it go with the hypotenuse first and then the legs, but when you see it written as an equation, it's usually the legs first. Regardless, this is our equation, a squared plus b squared equals c squared. This is our relationship that we get to work with. Remember, this theorem only applies to right triangles. It can be tempting to use it on any triangle once you learn it, but it has to be the case that you've got a right angle in there, otherwise this theorem is no good. And memorize this thing. It just never stops showing up. Basically, as long as you're taking math, you're going to keep using the Pythagorean theorem, so it's really good to just have it locked down. All right, so let's see an example of this thing. Say we've got a right triangle here with the two legs of being 2 and 4, and we want to find out what the length of the hypotenuse is. We don't know what the length of the hypotenuse is, but we want to figure it out. Well, according to the Pythagorean theorem, we have that a squared plus b squared equals c squared, right? Our two legs squared and added together equals the hypotenuse squared. So we look at the one that we're trying to figure out. We've got a leg of 4 and a leg of 2, so we've got 4 squared plus 2 squared equals that hypotenuse, that question mark, squared. Now, question mark's kind of a little bit weird to work with, so let's swap it out for a variable. Let's just call it h for the hypotenuse, right? The side we're trying to figure out. So we got 4 squared plus 2 squared equals h squared. Then from this point, it's basically just a matter of doing simple algebra, right? 4 squared plus 2 squared equals h squared. Well, 4 squared, that's 16. 2 squared, that's 4, equals h squared. We put those together, we've got 20 equals h squared. We can take the square root of both sides to be able to get to what the h is. So that's root 20 equals h. What's the square root of 20? Well, we can break 20 into 4 and 5, so we've got square root of 4 times 5 equals h. 4, well, that's 2 squared, so it pops out, and then we've got 2 root 5 equals h. We've figured out what the hypotenuse is. We're done here. So that's how you use the Pythagorean theorem. Now, let's have just a real quick refresher on working with square roots. Often when you're working with the Pythagorean theorem, it's going to involve using square roots because you've got all those squares going around. So how do you simplify square roots? You want to break a number into the factors that make it up. Look for squares that are under the radical that you can kind of pull out of the radical. Let's see an example of what I'm talking about here. Right, say we've got root 63. We're trying to find the square root of 63. Well, you can break 63 into 9 and 7, right? 9 times 7 makes 63. So now I've got square root of 9 times 7. Well, hey, 9 is the same as 3 squared. So 3 squared, we can pop the 3 out from the 9, have it come out of the radical. Now we've got 3 root 7. Now, an alternative way to be able to do this is you could use a calculator, right? If you're allowed to, you can use a calculator. So you can just take your calculator, punch in what's square root of 63, boom, you get 7.9372539. Now notice that's not actually what root 63 is. It's a really, really good approximation. Root 63 is roughly 7.9372539, and probably you'll get even more digits when you're working with your calculator, but that's not exactly what it is. It's close to the precise number, but the precise number is something that we can't even express by just writing it out with decimals. We actually have to write it out with that square root if we want to talk about exactly what it is. So we have to talk about it as 3 root 7. Now, what if you want to check your simplification, right? It's your first time doing this sort of square root simplification. You're not totally sure you got it right, or it's an important test. Well, what you can do is you can use your calculator, take square root of 63, because you know that's what you're working with, and you get 7.9372539, and then you say, hey, what did my simplification come out to be? It was 3 root 7. So you use your calculator and you do what's 3 times root 7 on your calculator. You do that with your calculator and you get 7.9372539. Hey, they're the same number. They're the same number. It checks out. It means since you've got a match between taking the square root of just the big number and then also taking the square root using your simplified version, if they come out to be the same thing, you can trust that you did it right. You got your simplification right. All right, so going back to the geometry part, what if things were the other way around? What if we had the triangle and we knew what all the sides were, but we didn't know if it was actually a right triangle, right? We knew what A was, we knew what B was, we knew what C was, we had numbers for all of them, but we didn't know if we were looking at a right triangle. Well, great news! The Pythagorean theorem works in reverse. And by that I mean you can check and see, is that equation, that a squared plus b squared equals c squared, is that actually true? Does that work out? And if it does, boom, you know you've got a right triangle. We can go the other way with it. And when a theorem works in reverse, or we can go this backwards way with it, we call that the converse of the theorem. So if you can ever take a theorem and go the other direction, the in reverse direction, it's called a converse. So the converse of the Pythagorean theorem, once again in that sort of math textbook kind of writing, given a triangle, if the square of the length of the longest side equals the sum of the squares of the other two side lengths, then the triangle is a right triangle. So once again, let's try to decode that real quickly. We've got A, B, C, right? C for hypotenuse, A and B for the two legs. So if c squared equals a squared plus b squared is what we've got here, the square of the length of the longest side, so c now represents our longest side, not actually a hypotenuse, but if the square of the length of the longest side equals the sum of the squares of the other two side lengths, then the triangle is a right triangle. So if we've got c squared equals a squared plus b squared, then we're looking at a right triangle. And once again, you'll often see it written out in sort of words in a math textbook with the hypotenuse coming first, so it's c squared equals a squared plus b squared. But in reality, you'll usually see all the equations using a squared plus b squared equals c squared, where it's the leg part coming first. Doesn't really matter which way, but the important part is if that equation works out, like a squared plus b squared does match to what c squared is, boom, you know you've got a right triangle. And also a corollary that comes from this is that a squared plus b squared not being c squared means that you don't have a right triangle, right? If you have that a squared plus b squared makes a different number than c squared makes, then you're looking at something that is not a right triangle. So let's see a quick example of the Pythagorean converse in action, right? What if we've got a triangle? We don't know if it's a right triangle, but we want to find out, where we've got legs of 2 and 4 and a hypotenuse of 2 root 5. According to the converse, if a squared plus b squared equals c squared, then we know we have a right triangle. So first we have to identify what's our c, what's our longest side. Well, 2 root 5, that's actually going to be longer than 4. We can also kind of see that from our picture here, although sometimes on a standardized test, you don't want to just assume the picture's telling the truth. So if c is 2 root 5, then we know that a and b have to be the 2 and 4. So we've got 2 squared plus 4 squared is questionably equal to 2 root 5 squared, right? We don't actually know that that's true. Notice I've got that question mark over the equal sign, and that's specifically there to point out we don't know that this is equal, right? We don't know that a squared plus b squared is c squared. All we know is that we're trying to figure out if this is true or not, right? We're trying to figure out, is 2 squared plus 4 squared the same thing as 2 root 5 squared? So moving forward with this, what's 2 squared? That's 4. 4 squared? That's 16. And then 2 root 5 squared, well, we can sort of put that square onto the 2 and the root 5, so we've got 2 squared times root 5 squared. 4 plus 16, that makes 20. 2 squared, that's 4. Root 5 squared is 5, right? You square square root, you get what's underneath the square root. So we've got 20. Is that questionably equal to 4 times 5? Yeah, 20 equals 20 at this point, right? 4 times 5 makes 20. So we've got the same number on both sides. It is the case that a squared plus b squared equals c squared. It checks out. So since it matches up, we know we've got a right triangle on our hands, right? As soon as you see that the legs squared and added together matches the same as the hypotenuse squared, then we know we're looking at a right triangle. On the other hand, if we'd gotten the case that the 2 legs squared and added together made a different number than the hypotenuse squared, then we'd know that we are not looking at a right triangle. We'd have something different. And in fact, we can even go farther with this and figure out what kind of triangle we're looking at beyond it just being a right triangle, but we'll save that for a different video. If you check out the advanced understanding, you can learn more about that there. All right, that wraps things up. Thanks for watching. And don't forget to check out the other videos on this topic over at chipmunkmath.com. See you next time.